that you can all hear me well. And welcome to our community and to this workshop. Welcome to our great speaker, Derek, and the community of AI Camp from Austria and to Gil too. So let me start it just uh, by presenting our community. First of all, you are all muted due to the very large audience. But you can type your question if you need to ask the question. Good morning, all, and I hope you are safe during this pandemic. Thank you for joining us today to this workshop to learn how to build a deep learning using TensorFlow model, using TensorFlow and Keras. Um, so before we get started with our workshop, I want to just to give a quick presentation of AI, our community AI Camp, and few announcements. So AI Camp, with the mission of making AI available to all developers, is a global online AI platform for developers, data scientists to learn and practice AI via online tech talks, workshops, and bootcamp and crash courses. So our goal is to enable everyone to learn AI from anywhere and anytime. We are one of the largest AI tech communities in the world, with more than 1 million developers in the group. We also have a local study groups in more than 50 cities in the world and 15 in more than 15 countries. So let me just introduce our local chapter here in Paris. So here is me, Khalida Douzi. I am a PhD in biomedical informatics and data scientist, and I'm working actually in Altron Lab here in France. And Adish, also he is a data scientist, and we are a local chapter here in Paris for AI Camp. So our community mainly focus on one live session with a real-time interaction to learn AI and machine learning by building projects and peer collaboration. So you can visit our websites to find more about our upcoming events. So our here are like some useful information for the session of today. So about question and question, you can type your question and we will answer it at the end of the session. The session is recorded. You can find it on the YouTube channel. So you can just search AI Camp. For more networking with our community and developers, you can join us on our Slack in this link. Now go back to our today's talk. We are so excited to learn with you, Derek, with our great speaker, about how to build a deep learning model to predict employee retention using Keras and TensorFlow. So Derek, just to give a presentation about you, he is a data scientist at Namespace Lab. He has a great passion for sharing knowledge, and he is a contributor to the data science community via blogs in Heartbeat towards data science, data.com, so you can find it online, his blogs. And he is also an author and online instructor. He is also trains and works with various institutions to implement data science solutions as well to upskill their staff. So without further ado, let me welcome our today's speaker, Derek. You can start whenever you are ready and take it away. Happy learning for all.
Thank you so much for the introduction.
Thank you. I'll let you share your screen.
Yes, please.
Yeah, that's mine. Yeah, you can do it.
All right, thank you so much. So in this session, we'll talk about building a deep learning model to predict employee retention. And so before we get there, I'd like to go through some key concepts in deep learning that would assist us in learning what we'll be doing in the code session. And so this is how we'll do this. We'll talk about just an overview of neural networks, then activation functions, cost functions, optimizers, back propagation. Then we'll now check the code review. And so as we all know that artificial neural networks are just computational models that have been built to mimic the workings of the human brain. And so for example, as we can see in this case, the dendrites, in this case, will represent your input data, and then the terminal actions would represent your output. And then at this place, the cell body, this is where you are, some function will run, which will generate this output. And so what you can see on this side is just a simple neural network with an input layer and one hidden layer, and then the output layer. And then you can also have more than one hidden layer. And so, for example, this is how the neural network would look like. You would have your input layer where you can input the input x1 all the way to xn. And so what would happen is that when the data is passed through the neural network, some weights and biases are initialized. And so these weights are what will be adjusted later for the neural network to learn. So this computation will happen at this place in the neurons, and then you'll get your output. And so we take a closer look at the computation that would happen at the neuron is that you have your input, which is multiplied by some weight, W, then you add some bias, and then you get your output. And so you can see now that if the weight is important to ensure that you do not get any, for example, zero values. Because if, for example, the value is 0 and you multiply by something, then if the answer will always be 0. So these weights and biases ensure that you never get to 0 values. And so what happens is that your weights and biases are initialized when you are running your neural network. For example, this could be a normal distribution, a uniform distribution, or they could be initialized to zeros or ones, and we'll see that later. Then an important thing to mention is that once this computation occurs, it is passed through what we call an activation function. And so now let's look at what an activation function is. So what an activation function does is that it will cap the output of your computation. So let's take an example. In this case, we'd like to predict whether an employee will leave a company or not. So it means that we want to get values between 0 and 1, because the probability of something will always be between 0 and 1. So we'd like to cap our outputs to numbers between 0 and 1. And so there are activation functions that would enable us to do that. And that's now the purpose of the activation function, to ensure that we're getting the output that we would like. And so there are various types of activation functions. And one is known as the ReLU, the rectified linear unit, and this one caps your output to be 0 and above, and this is mostly used in the hidden layers. And then we have the sigmoid activation function, which we can and will use for this exercise, because it's going to cap your outputs to numbers between 0 and 1, and we majorly use this for binary classification. And then we have a variant of sigmoid known as the Softmax activation function. And so if we are to recap this again, you notice that you input your values x1, x2, xn on the input layer. Some weights and biases are initialized, and they pass through the hidden layers where the computation is happening. And then in the hidden layers, you're using, for example, the ReLU activation function. And now in the output layers, since you want to cap your output, use, for example, a sigmoid or a softmax activation function. And so what's the difference between the Sigmoid and the Softmax activation functions? So for a Sigmoid, you majorly use it when your classes are non-exclusive. So for example, if you have an image, the image could have a car, a building, a tree, etc. And so just because there is a car in the image doesn't mean that we can't find, for example, a tree. So you use the sigmoid activation function when there is more than one right answer. But now for the softmax, you use it when your classes are mutually exclusive. For example, a picture can either be grayscale or colored. So when you only have one right answer, you then use the softmax. And so now the question is, how does your network learn? And so what would happen in this case is that, for example, when you get your output y1, this would be compared with the actual value. So when you get your outputs, you compare this with the expected outputs. And so you check the difference between the predicted value and the actual values. And so what you do is that you would like to adjust the weights so that this difference between the predicted and the actual values is as low as possible. And so we do that using what we call the cost function or the loss function. And so the choice of a loss function or a cost function would depend on, for example, the problem. If it's, for example, a classification problem, using the binary, using the log loss. If it's, for example, it's the regression problem, using something like the mean squared error. So the choice of a loss function would obviously depend on the problem. And so, for example, when you're doing this, your loss function should be decreasing. So for example, in this case, as you can see in this graph, the loss function is decreasing. As you can also see from these epochs, the loss function is decreasing. So in the event that your loss function is increasing, then it means your network is obviously not learning. So you need to always plot these kind of graphs to check whether the loss function is decreasing. And so other ways you can do this is, for example, using a callback. For example, in Keras, you can use the early stopping callback, and this would stop the network when it stops learning, so that you don't need to monitor the loss function yourself. There are times that in your network, you may notice you have null values or NANs in your loss function. And so obviously this would be caused by if you have NANs in your dataset, or if your dataset is not scaled, because you know that in deep learning, we need to scale the dataset, the values in our dataset. This is obviously because even when the weights are initialized, they're initialized to small values. And so we scale the dataset so that we can also have the small value so that the network would be able to learn. And then also operations that lead to NANs would also lead to NANs in your loss function, in your loss values. So for example, division by 0 or the square root of a negative number. And so how the weights are adjusted is through what we call an optimizer function, or what we call a gradient descent. And so the goal is always to find the place where the error is minimum. And so that's the purpose of the optimizer function. Its goal is to adjust the errors by reducing the cost function. And so as you can see in this case, this distance is what we call the learning rate. And so at this point, this is the ideal point you'd like to be at, where the error is as low as possible. So what would happen is that once the errors have been calculated, so this now will be propagated back to the network, and then the weights would be adjusted. And so there are various variants of gradient descent. One of them is known as the batch gradient descent, where you use the entire dataset to compute the gradient of the cost function. And this is obviously slow because you have to compute the gradient of the entire dataset for you to perform a single update. And then we have what we call the stochastic gradient descent, where you compute the gradient from a single training example in every iteration, which is obviously faster. And then there's also the mini batch gradient descent, where you can use a sample of the training data to compute the gradient of the cost function. And so we've, in this short overview, we've seen the neural networks, how we use them, the overview of the neural networks, activation functions, optimizers, and back propagation. And so if there's no question so far in the chat, I think we can now check, we can now go to the code for this section. So I can see someone asking, is the loss function same as the optimizer? It's not. The optimizer function is what is used for adjusting the loss function. So now let's go to someone is asking what are the differences between TensorFlow and CNN. So TensorFlow is the framework we use for building networks, deep learning networks or neural networks. CNN is convolutional neural networks. So this is a type of a neural network. I hope this is clear that TensorFlow is used to build, TensorFlow and Keras is used to build the CNN. How to choose the number of hidden layers? We'll see that in the code, but there are so many ways of doing it. Let's go back to the code and then we'll see how we'll do this. So the article in question is this one here. So how to build a deep learning model to predict employee retention using Keras and TensorFlow. So the first step is obviously to import pandas and numpy. Pandas is for data manipulation, numpy is for scientific computation, and then we use pandas to load this dataset. So the way we do that is just by creating a data frame. df is equals to pd.readcsv, and then we pass in our data frame, and this is the data. df.head will just give us the first 5 values, and this is the first 5 values of our data. We have the satisfaction level of the employee, last evaluation, the number of projects, average monthly hours, then we have time spent in the company, whether they had a work accident, whether they left, and this is what we are interested in predicting, whether the employee will leave. And then we have promotion in the last 5 years, whether they were promoted in the last 5 years, the department, and the salary. And so as we can see, the department and the salary are not numerical, that they are categorical. And so we need to convert these to numbers because we cannot pass these strings to a deep learning model. So the way we do that is we'll just select these 2 columns, that is department and salary. And to convert them to zeros and ones, we use what we call pd.getDummies. So we're just creating dummy variables. And so what this will do is that it will convert these ones to zeros and ones. So for example, if we were to check this data, I mean this, if we were to check this, we'll notice that the departments, for example, so we have department RAND, then you have department accounting, department HR, department management. So each of these departments got its own column, and then 0 says that the person was not in that department, and where there is a 1, the person was in that department. And the way we achieve that is by using pd.getDummies. Then we pass in our data frame, the columns we'd like to convert to dummies. In this case, there are these 2 columns. And then drop first is equals true will mean that if, for example, you have, let's take, for example, you have categories A, B, and C. So drop first means that when these will be converted to dummies, one of these will be dropped. So A will be dropped because if someone was not in department A and was not in department B, then obviously they were in department C. If someone was not in department B, then it means either in department A or department C. So we can drop this and we'll be left with B and C. So this is something known as multicollinearity in deep learning or in machine learning. So it's always important to drop the first so that you do not have any problems. So now with that out of the way, we can now go to separating our training set and our testing set. So we know that in machine learning, we have to convert, we have to split our data set into a training set and a testing set. And so this is done using a train test split from scikit-learn. And this function, so before we do, we split it into a training set and a test set. What we'd like to do now is we create the X and Y. X contains the features, that is the features of this data set. Y contains the target, that is left, the column we are trying to predict. And so we are using dot values here to just give us the values, the NumPy arrays. And so now with X and Y, X, again, we are saying these are the features. Y, this is the target. So using that now, we can use the train test split, which will take in X, the features, and Y, the target, and then we pass in a test size. So in this case, we want to use 30% of this data for testing and 70% for training. And so what we can see is that when you use this function, it will give you X train, X test, Y train, Y test. So X train and Y train will be used for training. X test and Y test will use this for testing. So once that is done, once now we have our training set and our testing set, we have to transform our data. And so in machine learning, we need to convert our data set to small numbers. And the way we do that is by pre-processing this data set. And there are many ways of pre-processing, and one of them is the standard scaler. And if we were to even check this documentation, we can see that it says the standardized features by removing the mean and scaling to unit variance. So this is just one of the ways. There's another way where you can just convert them to numbers. This is the standard scaler. You can also use, there are other scalars we can also use, but in this case, let's just stick with the standard scaler. So the way you do that is by creating a variable saying SE is equals to standard scaler. So we're just creating an instance of the scaler. And then after that, we now transform our data set. And so the way we do that is by using sc.fit transform. Then you pass in the training set. So fit means at this, when you say fit transform, it means that it's going to fit this scalar to our data set, that it's going to be learning the parameters needed to transform it, and then transform will just transform it. If you do not use fit transform, then you'd have to first of all do fit and then do transform later. But then doing fit transform will just convert, will do this for you in one line. And then for the X test, now we transform it. So we don't do fit transform in this case. Since the parameters have already been learned, we don't need to fit them again. So at this point,
Derek, sorry to interrupt you. Actually, there are a lot of people asking for the Collab link and also for the link to the data sets. If you can share it please.
Sure, no problem.
Thank you.
Do I put it on the Q&A or on the?
Maybe on the chat.
Let me. Okay, I've posted it there. Do you mind posting it on the Q&A?
Yeah. Okay. Thank you very much. Okay.
So let me go up and get the data set. Posted on the panelists chat.
Yeah. Yeah. Okay. I will send it to. Okay. Thank you very much, Eric.
Okay, so we can proceed. So at this point, we had a split of a data set into a training set and a test set. We'd also pre-processed it, that is, we'd transformed it using the standard scaler. And so now at this point, we are ready to build our neural network. And so now this is where Keras comes in. And so in this case, we import Keras, and then we import sequential, we import dense, and then we import dropout. So sequential is what will initialize initialize the layers for us. Then dense is what we use for creating the dense layers, and dropout is what we use for dropping some connections in our network to avoid overfitting. So let's go through creating this network using Keras. And so the first thing is we create a variable called a classifier. I also believe that you might not have access to this notebook, so I should just grant access. So I believe this should be the link that everyone should be able to access. Let me posted it on the Q&A.
Yes, please.
Sorry for that. So what I was saying is that we create a classifier using sequential. And so now once we have this sequential, that is, we've initialized the layers, a linear stack of layers, what we can do now is use now classifier.add to add the layers that we want. So in this case, we add our first layer, dense, with 9 units. The initializer here is the uniform, that is to initialize the weights to small values with the uniform distribution. And the activation function we're using is the ReLU activation function. So this is majorly used in this this layer. And then the input dim, that is 18. So we have 18 features in our data set. So for the number of neurons, as you can see here, we've used 9. And one of the ways of selecting this is just an average of some number between, that is the number that is not above this 18. So for example, we can choose a number between 1 and 18, or we can also choose a number that is close to the average of 18 plus 1, that is the output, so that is 19. And so this is just one of the ways of doing that, but there are other ways of choosing the number of units. And so I can also add a dropout layer. This will drop 1% of the connections in the neural network. So this is just to ensure that we do not overfit. So this is one of the ways. you just force your network to learn. And then finally, what we do now is we add our output layer. And for this, we know we need just one output. So whether the employee will leave or not. So that is why we have just one, still using a uniform distribution for the initializing of the weights. And in this case, the activation function is sigmoid because we just want to get that output, whether someone will leave or not. If, for example, you're doing, for example, the MNIST, you'll notice that the activation function in this case is the Softmax activation function. So once this is done, you need to compile your network. So at this stage, this is where the gradient descent is applied. This is where your network, this is how the network lands. And that's what we were talking about, the optimizer. And so we use the Adam. Adam is the most common optimizer function. So whenever you do not know even which optimizer to use, it's always good to start with Adam. And since this is a binary problem, we use the binary cross entropy, and then we're passing metrics as the accuracy. That is how accurate our model is. With that out of the way, we just feed that to our data. So we feed it to the X train and the Y train. Batch size is 10, meaning that 10, we want to, in every epoch, the batch sizes will be 10, and we're just doing one epoch in this case. And once you've trained your model at this point, you can run your predictions. And to do that, you just say classifier.predict. And then you pass in the training set, X test, X. This is the X test. That is the data we use for testing. And at this point, if we were to check this, we would notice that we do actually have our predictions. So this is showing false, 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 and true because this has already been run. And what this is doing is that we are capping our predictions. That predictions above 0.5 will mean that the person is will leave, and those less than 0.5 will mean that the person will not leave. So this is how we are capping them by saying the predictions. This prediction here widespread. For any predictions above 0.5, this will be true. And if it's less than 0.5, it's false, meaning the person will not leave. And so we can also check the confusion matrix by importing it from scikit-learn metrics. And so for the confusion matrix, you pass in your y-test and the predicted values. And what the confusion matrix basically does, it shows you the predicted values. I mean, the true positives, the true negatives, and so on. But a better way of just looking at this is using the classification report, which will give you the precision, recall, F1 score. And so you can see that this accuracy is this one here. And so how would we go about, for example, making a single prediction? So in order to make a single prediction, you need to pass in a single, for example, a single column, which also needs to be transformed. Since we were transforming the training values, also need to transform this, and we pass it as a numpy array. So this is just a single column that you pass, and then you can see that this one, the prediction was false. And so let's see how we could work on improving the accuracy of the model. And so we can do this using the grid search to search for the best parameters. And we can also apply cross-validation. So to do that, we use the Keras classifier and cross-val score to just check the performance. So we create a function known as make classifier. And what you notice is that this is similar to the classifier we defined above. So there's no major difference. We're just making this into a function, and when we are returning this classifier. And so now using Keras classifier, so we say our classifier is equals to Keras classifier, and then what we need to pass in the build function is this classifier, batch size of 10, and then one epoch. And the way we can check our accuracies through cross-validation is by using this cross-val score. And then our estimator in this case is this classifier here. So we pass this classifier. X is the X train, Y is the Y train. And then we use the CV as 10. So dividing our data set into 10 groups. Then n jobs is equals to -1 means that we'll use all the CPUs available. And so if you check the mean of the accuracies, you will see it's 0.83 and a slightly and a very low variance. So which means we're not doing very bad. And so next we can check at tuning our parameters. So the way we can do an exhaustive search of the parameters is through the grid search CV, and we'll use the same make classifier, but then the grid search, this grid search CV will be used for searching for the best parameters. So again, once again, we define our classifier using Keras classifier is equals to build function, which is the make, which is this classifier here. And then now we define the parameters we want to search. So we want to search for we want to search batch sizes of 10 over 20, 35, and 50. We want to search epochs 2, 3, 4, 6, and 10. And for the optimizers, we want to try the Adam and then the RMS prop to see which one will give us the best parameters. And so the way we do that is by using grid search CV. We pass in our estimator. In this case, it's this classifier. And then param grid is now these parameters. This is what will be searched. And then we are checking the accuracy. Again, the cross-validation we're using 10. And if, for example, if you'd like to learn more, for example, about this, you just over and then you can see that it's giving more information about this, including parameters, the estimator, the parameter grid. This you can always read this to get more information on the specific function. So this will give you all the information you need. CV, for example, it determines the cross-validation splitting strategy. So if you put none, it'll use the default 5-fold cross-validation. If you put an integer, you're specifying the number of folds in a stratified k-fold. So what you're doing in this case, we're passing in 10. So we're using 10 stratified k-fold. And so once that is done now, once you have your grid search, you fit it onto your data set. And something that is important to note in this case is that there is this parameter here known as refit is equals true. And so what this means is that once the search found the best parameters, it will refit this to your training set. And so your classifier will be ready to use, so you don't need to go and refit it again. And we'll see this in a moment. So in this case, we just fit it to our training set. And so now to get the best parameters, we use the grid search dot best params. And in this case, the best parameters we are getting is a batch size of 35, 10 epochs, and optimizer of Adam, and the best accuracy at 95. And so at this point, the data set has the grid search has already refitted these best parameters on our data set. So we don't need to fit it again. So we can actually just move forward and make our predictions. And so by so doing, we see that from the classification report, we are able to get the classification report with an accuracy of 96. Do we have any questions?
Yes, actually we have some questions. Um, so, so the first is, can you make a comparison between TensorFlow and PyTorch? Um, Derek, can you hear me?
Sorry, yes, you
Yeah,
said something between Python and PyTorch,
yeah, exactly. Yes, this is the first question.
or like the choice between PyTorch and TensorFlow.
Yeah, yeah,
So that I would say it's a matter of preference because they're both good tools. They are open source, so I'd say it's a matter of preference. Depending on the one which you actually think is better for you or easier for you to use. So I'd recommend you just try both of them and just decide on one.
okay. Uh, Thank you. There are like more questions. So second one is, why epochs equal 1?
So for that, I was just using one epoch for illustration. Doesn't mean you need to use one epoch. So actually the best way to check the number of epochs is to use what we call a Keras callback. So what you do is, for example, you set your epochs to say even 1,000 or 600, and then you use, for example, it's known as the early stopping callback. And so what the early stopping callback would do is that it would stop training your network once the model has stopped learning. So that's the best way of doing it. You just use a Keras callback, and when your network stops learning, the network would stop training. So you don't need actually to specify the epochs
Okay,
by yourself. This was just a case for illustration.
okay, got it. Thank you. So third question is, aren't we missing validation data sets? Otherwise our model could be biased.
So that's true. We should actually include the validation set. And then once we include the validation set, what we can do is we plot the loss function, the validation loss and the training loss. Then we compare the two and then check how the model was performing. Obviously, we would not be able to actually go through every tiny detail in this session, but it's true. We would need to pass in the validation set, and then we plot the loss function for the validation set and the training set, compare those two, and see the performance of our model.
Okay, okay. Thank you. So we can choose like the size of validation tests according to the loss function.
So actually, if I want to show, let me show you this again.
Okay.
So what I believe he was talking about was at this point, if we were to check even the documentation for this, we should, at this point we should be able to pass in the validation data. That is, we would pass it, we would be able to pass it at this point.
Okay.
So I believe this is what he's talking about, and then we would be able to compare the loss between the two of them.
Okay. Yeah. So this was the question of Kasim. I think we answered. So we pass to the another question. Um, are there any feature engineering or data augmentation techniques that could be used in this case?
So in this case, for example,
For
looking
this
at
example, I think.
this is actually something we can think through together. Because, for example, this is your satisfaction level, you have your last evaluation, the number of projects, average monthly hours, time spent in the company, work accident. So, so for example, we can try and derive new features from this. For example, we could say for example, what's the ratio between the level of satisfaction in the last evaluation, something like that. And then, but then you'd also need to check whether it's improving the accuracy of the model or not, because you're not just adding features for the sake of it. So you add the new feature, and then you obviously see how it's affecting the model, the performance of the model.
Okay. Okay. So this is my question. Like data augmentation in this case for deep learning, it is about to add more features than not more examples for learning. That's okay. That's right.
Uh, so majorly my experience with data augmentation is, for example, in when you're using images,
Mm-hmm.
and so you're trying to, it's like you're creating new data points from the same data set. For example, if it's an image, you can, for example, rotate the image at 90 degrees, you can flip it. And so this is important, for example, in image recognition, to
Mm-hmm.
ensure that the network is able to see the image from different angles. So if it's,
Okay.
for example, it's that common example of dogs versus cats, that the model is able to see the cat at its as it's looking in front, on the side, like on all angles, so that it becomes much better at predicting,
Okay.
like showing the images at different angles.
Okay. Thank you very much, Derek. So, a second question, another question. So, grid search CV looks good for small data sets. How about large data sets? How can we handle that?
So one of the ways to do that is, for example, to use Google Colab, because you can take advantage of the GPU and TPU processing. So if you have a large data
Okay.
set, ideally you want to use, for example, a GPU machine, which can be provided by, for example, Google Colab, or you can try using Dask. Dask is good at dealing with huge data sets.
Okay, perfect. Another question, how about using AutoML?
I haven't tried AutoML on this specific data set, but this is something that you can obviously try.
Yeah.
Because there is the auto Keras. So definitely feel free to try auto Keras on this and see uh, the difference.
Yeah, and maybe share with us your results in order to have this comparison. And another question: are you using TensorFlow or Keras? So I think both of them, right?
Yeah, obviously Keras is built on top of TensorFlow, but currently at this current state, TensorFlow, Keras is the official API in TensorFlow. So when this article was written, that was not the case, but at this point, as we're speaking, Keras is the official API for TensorFlow.
Okay, perfect. Another question. So in the first classification report, we get precision of 0 for class 1. What does it mean? How we can prevent from this situation?
So one of the instances where you were majorly concerned with the precision, the recall, the F1 score, this is obviously on a case-by-case basis. In the event that, for example, your data set is, let's say the data set is imbalanced, then accuracy is obviously not a good, it's not a good way of, accuracy is not a good measure in that case. So if your data set is quite imbalanced, then it's better to use, for example, the precision, the recall, and the F1 score. And so optimizing this precision recall is obviously on a case-by-case basis. So a good example is when you're using, for example, trying to predict that someone has diabetes or not. So a question is, would you better tell, is it okay to tell someone who doesn't have diabetes that they have diabetes? Or is it better to tell someone who doesn't, which would you prefer? Telling someone who has diabetes that they don't have diabetes, or telling someone who has diabetes that they don't have diabetes? So the choice in the precision, the recall, the F1 score is actually, it's a business decision. So it actually depends on a case by case. I hope that was a bit clear.
Yeah, I think it's clear. Otherwise, they can ask more questions about that.
Sorry?
So another question is about does the Keras sequential classifier always create fully connected layers?
Sorry?
Um, do you hear me?
Yes, I can.
Okay. So another question is does the Keras sequential classifier always create fully connected layer?
So the sequential actually is not creating the layers per se, but it's initializing the layers. The layers are created using dense, and dense creates layers that are fully connected.
Yeah.
But you can drop some of those connections using a dropout. So, for example, when you want to reduce overfitting, you can use a dropout for that.
Okay. Okay, thank you, Derek. Move to another question. What additional steps could be taken to improve performance?
Obviously, the obvious ones were one, of course, using more training data. That's one obvious one. You can always use more data to improve the performance.
Yeah.
Obviously, our even in our grid search, it doesn't mean that we tried all possible parameters. One could also try different number of epochs, different number of batch sizes. So even at this grid search, someone could try using more parameters. Try maybe a different optimizer, different epochs, different batch sizes, and see the difference you would get.
Okay, perfect. So we have another question. I think the last one from Farouk. Farouk, we missed this question, so sorry. So he asked it, since we are using scikit-learn split method, what if the test set contains some data points that is kind of the outlier? There is a representative data in the training set in terms of the training set. How much will it affect the model performance? I don't know if it is clear.
So the question is actually clear, and there are two ways, in my opinion, of dealing with that. Number one is if you notice that there are outliers, you could remove them and
Mhm.
work without them and see how the model will perform. And then you could work with the outliers and see how the model performs and see, is it better to leave them or to remove them. But it shouldn't be a major problem since since all the points will be scaled at the pre-processing stage. But it's obviously something we can remove, train the model and see the performance, and then train the model again with outliers and see what the differences would be. I hope that is clear.
Okay, thank you very much, Derek.